Hi, so I'm Callum, and in this short presentation, I'm going to give you a preview of the talk that I was originally scheduled to give at last year's JEC World Composite Challenge. And in this competition, myself and 10 other PhD students from around the globe are competing to convince a panel of industrial experts of the value of our research with 5 minutes and 1 slide and no animation. So with that, here's a little taster of my PhD thesis, which is titled Cans from Dynamic Bonds to Sustainable Composites. So if I draw your attention to the top middle of the slide, I've got a diagram of a simple composite part, a skin and stiffener here, but it could be anything. If we think of our composite part in terms of a life cycle, then we can state that there are going to be several points at which we're generating significant waste. So one, in manufacture, due to defects and offcuts, there's going to be scrap. In service, damaged parts are going to result in scrap and waste as well. And at end of life, because currently there aren't any commercially viable recycling methods with conventional composites, we're going to probably incinerate or landfill our composite as well. So there will be waste there too. So clearly there's a bit of a sustainability issue in the composites industry, and that's not unique to us by any means, but we should probably try and do something about it going forward. So one such way in which we could create more sustainable composites in the future is replacing conventional polymers that we use as our composite matrices with covalent adaptable networks, or CANs. And what these are essentially a type of polymer that lies somewhere between the two main classes of polymer, thermosets and thermoplastics. So in this diagram here, the white circles represent the polymer backbone, and the blue circles binding them together are the crosslinks. So structurally, they're similar to thermosets, but the difference is these crosslinks contain a reversible chemistry that, when activated, allows them to decrosslink or depolymerize well. So if we think about this applied to a self-healing concept, in this diagram, you can see that if we have the polymer and it's subject to some damage, perhaps an impact, this could result in perhaps some microcracking on a molecular level. This could look something like this. And if we want to repair this, we could deliberately decrosslink the polymer by applying a stimulus, such as heat or light, to the surrounding area. And as a consequence, the crosslinks will break. And then this gives the surrounding polymer a really massive drop in viscosity, which allows the polymer chains to flow, to fill cracks and repair damage. When we remove the stimulus, the crosslinks can reform and restore the mechanical performance we had to begin with. So that's the concept of CANs, or covalent adaptive networks. In terms of thermomechanical performance, these materials look a little bit like these graphs I've shown here. So this is one example of a CAN that I've made in terms of DMA and rheology. So looking at the DMA result, you can see that at low temperatures, up to 70 degrees or so, we're dealing with a stiff material, not too dissimilar from a conventional epoxy, and this is highly brittle. And then when it is heated, in this case, as the stimulus, it decrosslinks around 100, 120 degrees, and what you end up with is a viscous liquid. If we repeat this process many times, as shown by the cyclical rheology here, as decrosslinking, recrosslinking, and so on, therein is the value here. So if we apply a polymer such as a CAN like these into our composite part, then hopefully we can improve sustainability in a variety of ways, which I've illustrated in these boxes. So if we look at the manufacturing step, we can perhaps increase our sustainability and reduce waste there, in the fact that we can repeatedly reshape our composite structure, our panel, or whatever. If it doesn't work the first time, we try it again. It's still got the active chemistry in there. So just because it went wrong the first time doesn't mean it's going to be scrapped. Two, in service, if we have a badly damaged panel or whatever, we can use a self-healing process like the one I sort of described for this graphic up here. And I've given this some photos of some 3-point bend testing here. So the healing efficiency with these polymers can be really good, actually. I've deliberately included this somewhat misleading low value of 28% here as a reminder that one thing we can't do as with all healing technologies, is repair fiber damage at the moment. And finally, at end of life, we can also do a couple of things to improve sustainability. A key one being developing novel recycling processes. So what you can see here is a simple solvent-assisted recycling process I've developed, which enables us to easily separate the polymer and the fibers such that we can reuse them to create valuable products. And finally, maybe we can use these polymers as well as reversible adhesives to easily disassemble complex structures. So hopefully with that, I've convinced you there is some potential great value in using cans to create more sustainable composites in the future. And I would like to thank you for listening and direct any questions you may have to my contact info